Okay, I think we'll go ahead and get started now. Can everyone see the slides and hear me okay?
Yes.
Thank you. Okay, so what we're going to do today we're going to start on chapter 8, which is chemical bonding, and then about 9 o'clock we'll stop, and then you can start the quiz. A couple things I want to say about the quiz. In the quiz, you're going to have to write out some chemical equations, some reaction equations. And so in that, instead of using the arrow going between the reactants and the products, just use the equal sign. So when you type that in, your answer's in, don't worry about finding the arrow, just say, put the reactants on the left, and then put the products on the right and put an equal sign between them. So, okay, so in chapter 8, we're going to start talking about chemical bonding. You got a little bit of this recently in the last 2 computer labs. So some of it, hopefully will look a little bit familiar to you. So when we talk about chemical bonds, what we're talking about are 2 atoms or ions that are held together in some fashion. And there's 3 basic types of bonds. One is ionic. And that, in an ionic bond, what you have is you have an electrostatic attraction between oppositely charged ions. So once again, our old opposites attract taking place here in an ionic bond. A covalent bond is where you're sharing electrons between the atoms. So that's what we were looking at in some of that last lab with the bonding. We're looking at how the electrons are shared. And then finally, there's metallic type bonds. And this is where the free electrons around the metal atoms hold those metal atoms together. The second one, the covalent bonding, is by far the most common type of bond that we see. So Lewis developed a way to kind of demonstrate how the bonding occurs through the potential bonding electrons using a dot structure, or a Lewis structure, as it's called. And so what you do is you use these little dots. And like I said, we saw this in the last lab, those dot structures or those Lewis structures. We use a dot to represent a valence electron around each of the elements. And so when we form compounds, the atoms either gain electrons, lose electrons, or share electrons. So in our Lewis structures, when we draw them, we draw the dots as either being lost or gained or shared. And what you're trying to do is around each of those elements, get it so that each is surrounded by 8 valence electrons. And that's known as the octet rule. So when you draw the dots, each of those elements, the goal is to have 8 electrons around it. Down at the bottom here, we see a portion of the periodic table where we see the groups 1A through 8A listed. And then we have the electron configurations. And then below that, you see the Lewis symbol. By Lewis symbol, it just means for that element, how many of those dots or how many valence electrons are around it. What you'll notice is that the group number 1 through 8A, that tells you how many of these dots or these valence electrons are around the element that's in that column. So for instance, the 1A group, in this case, we see lithium and sodium. What we notice is that each of those, lithium and sodium, have one dot, one electron. We go to 2A, those have two dots, 3A, 3, on down the line. So by looking at the periodic table and seeing what group it is, in other words, what column it's in, and seeing what that number is, 1A, 2A, 3A, 4A, on down the line, that tells us how many dots, how many valence electrons, when we draw these Lewis structures, tells us how to start that. Let's talk about ionic bonding a little bit. So when we have ionic bonding, we're almost always talking about an interaction between a metal and a non-metal. So in other words, those things on the left-hand side of the periodic table interacting with the things that are on the right-hand side of the periodic table. The one exception is that group 8A. And remember, group 8A are the noble gases. And so those aren't very reactive, as we talked about before. So that's why we're going to exclude those from this discussion. So in the ionic bonding, remember the other thing that we talked about with metals and nonmetals is metals like to give up electrons or donate electrons, and nonmetals like to accept electrons. So this type of bonding is called an electron transfer type bonding, because you're typically transferring an electron from the metal to the nonmetal. And remember, metals tend to have positive charges. Nonmetals tend to have negative charges. So once again, that's reflective of that movement of electrons. These types of reactions to form these types of bonds are usually exothermic. So if we think about this in terms of ionization energy and electron affinity, the things we learned last chapter, then that element, the metal that likes to give up the electron, has a low ionization energy. And the nonmetal, which likes to pick up the electron, it has a high electron affinity. So those kind of properties that we talked about last chapter factor into how this ionic bonding works. So below here at the bottom, we have an example of sodium and chloride, how they would do that electron transfer reaction. And so we see sodium in that 1A group has the one dot, or the 1A, rather the one electron. And then the chlorine, which is in the 7A group, has 7 dots or 7 valence electrons. And we see that the sodium gives up that electron to the chlorine, chlorine accepts it, and now we have sodium with a plus on it to designate that it's lost that electron, plus the chlorine, and we draw now the chlorine with all 8 of those dots around it, all 8 of those valence electrons around it, and we put a parentheses around it and give the whole thing a minus. And that minus tells us that it's picked up an electron. So that's the kind of transfer of electrons that you typically see in this ionic bonding. So some of the properties of ionic substance is that they tend to have pretty well-defined 3D structures. And so there's techniques that are out there that you can look at the structure, the 3D structures of materials. And so if you look at these ionic substances, they tend to be pretty well-defined structures. There's an example of kind of a cartoon drawing of sodium chloride, where you have a nice pattern of sodium and chloride atoms in that lattice. Ionic substances tend to be brittle, they tend to have high melting points, they tend to be crystalline. And usually you can break them along clean lines in that lattice structure. And we'll talk about lattices here a little bit more. So in this slide, it just kind of walks you through the different steps of doing this type of ionic bonding, where you start with the metal, and the metal is usually a solid, and the non-metal is usually a gas. In this case, it's sodium is the solid, and chlorine is the gas. Then you convert them both to gaseous atoms. Then you convert that to ions. So that goes back to that ionization energy and electron affinity values. And then you combine. So it tends to be a multi-step process like this. And so you have energy levels associated with each of these steps. It takes energy to convert elements to atoms. So that's an endothermic step. Then it takes energy to make a cation. That's another endothermic step. And then energy is released when you make an anion. That's an exothermic step. So you've got some endothermic steps in the process. You've got an exothermic step. But then that formation of the final compound, that's very exothermic. And that kind of dominates things. And so because that energy release is so great, the overall reaction will turn out to be exothermic. And that's what you see on the diagram here on the right. We see that that's a net exothermic reaction. So this brings us to something called lattice energy. And lattice energy is a term that we use when we talk about these ionic compounds and these ionic bonds that they're involved in that. So the main reason that these ionic compounds are stable is that there's an attraction between the ions. So remember, we say opposites attract. So we have our negative ions, we have our positive ions. An example we just had was sodium was the positive, chlorine was the negative, chloride was the negative. So you have that opposite charge attraction there. And so what lattice energy is simply the energy that you would need to completely separate 1 mole of the ionic compound into its gaseous ions. So in other words, how much energy would you have to put into that to overcome the attraction energy that stabilizes things? So down here at the bottom, we see for sodium chloride, if we had solid sodium chloride and we wanted to separate that into the sodium plus gaseous ion and the chloride minus gaseous ion, then it would be 788 kilojoules per mole. So, and note that because we're having to put energy in to break apart the bonds, in this case, the attraction between the opposite charges, that it's a positive value. If we go the other way, so if we were going to make the sodium chloride, so in other words, take the gaseous sodium ion, gaseous chloride ion, combine those, then that would be 788 kilojoules also, but it would be a negative value because that would be an exothermic. So if we're decomposing the ionic compound, that's an endothermic process because we have to put energy in. If we're making it, we need to change the sign on that delta H lattice value and reflect that it's an exothermic. So it would be minus, in this case, minus 788. So here are some example lattice energies for some ionic compounds. The bigger the number, then that means that requires more energy to go in to break apart that lattice interaction, that positive negative charge interaction. So the higher the values, the more stable it is and the more energy you have to put in to break it apart. So when we look at lattice energies, lattice energy tends to increase with the charge on the ions. So in other words, if you have a cation and anion that are both +1 or -1 charge, that's going to have a lower lattice energy than one that would have +2 and -2 charges on the ions. The other thing is the lattice energy increases with decreasing size of the ions. And so both of those make sense. If you think about the charge, you've got more electron movement going on. Remember, because we said in these ionic bonds, the cations are donating electrons, so you've got more electron movement. And then in terms of the size, as we decrease the size of the ion, there's going to be more of that interaction between the nucleus and the electron and the ions, and the electrons rather, and so that would keep things a little more stable as well. There is a formula here where you can do a calculation for this energy value, and as you can see, it involves the charges on the particles. So that would be that +1 or -1 or +2, -2, and then the distance between the centers. So this formula just reflects kind of what we verbally said. I think in this case, it's probably more important to remember the verbiage than worrying about the formula. So let's take a look at a couple of homework problems. The first one I'd like to just go over is 813. So in 813, it's asking you to write the Lewis symbol for atoms of each of the following elements. So aluminum, bromine, argon, strontium. So what you would simply do is you'd write the symbol for the element, so the first case aluminum, Al, and then you would go and you would look and see which group it's in. And so if we go all the way back here to where we have that little bit of a periodic table, oops, there we go. We see aluminum is in the 3A group. So that's that third group over, the kind of pinkish looking one on our slide. And so from that, we would know that there are three dots or 3 valence electrons that we would put on there. Bromine is a 7A element, so we would put 7 around that. Argon's 8 and strontium's 2, so we would put that. So pretty straightforward. So the key thing is just remembering that you need to look at the periodic table, see which of those groups it's in, 1A, 2A, on down the line through 8A, and start by putting that many of the dots around it. Let's take a look at 815. In 815, it wants us to diagram the reaction between magnesium and oxygen atoms to give the ionic substance magnesium oxide. And then it asks how many electrons are transferred. So once again, just as we did in the last question, we would write the symbol for the element. Then we'd look on the periodic table to see how many valence electrons are around that atom. And in this case, magnesium has 2, oxygen has 6. And since it's an electron transfer reaction, and we know that magnesium likes to be +2, oxygen likes to be -2. So we take the 2 electrons from the magnesium, put those onto the oxygen. So now we write the magnesium as Mg with +2 superscript, and then the oxygen picks up those 2 electrons that came from magnesium. So now we've completed that octet for oxygen. And then we put a parentheses around that and then give it a -2 charge. So our charge is balanced, +2, -2, that's good. We've shifted those electrons. And so in this case, it's a 2 electron transfer reaction from the magnesium to the oxygen. Let's take a look at another electron configuration one. So we want to start by writing the electron configuration for each of these. And then what we do is then we decide what kind of ion it is. So in this case, some are positive ions, some are anions, so negatively charged. And then we reflect a change in the electrons in that electron configuration based on what type of ion it is. So the first one, strontium, we write that. We have our noble metal core. And then we have 5s2. So we have 2 s electrons there. It's a +2 ion. So if it's a cation, in this case, a +2 ion, then we know we're losing 2 electrons. So we would lose those 2 5s electrons, and we see that gives us a noble gas core. In B, we see we have 4s2 and 3d2 as the valence electrons. Once again, we form a +2 ion. And remember, when we lose 2 electrons like this, we lose them from the highest, think of it as the highest principal quantum number. And so that's why we lose the 2 s electrons, because that quantum number is 4. So it's a higher energy than the 3 for the d electrons. So in that case, we lose the 2 4s electrons, leaving us with the argon core electrons and then 3d2. So we don't get a noble gas configuration with this ion. In C, for selenium, we have argon core, then 4s2, 3d10, 4p4. In this case, we're forming an anion. So since it's an anion, it means we're picking up 2 electrons. And so in that case, those electrons would get added to the 4p level, and that would give us 4p6, and it would fill out that whole p orbital, and then that would result in us having the same configuration as Kr, the noble gas. And then the fourth one, nickel, once again, we have that 4s2, 3d8 electron configuration. If we make the +2 ion, we're going to lose the 2 electrons from the 4s orbital. So take a look at some of the other problems and get comfortable with doing some of that electron movement, writing the electron configuration, kind of matching it up with the valence electrons and things like that. So let's talk a little bit more about electron configuration of ions, which is kind of what we were doing in there. So the main group metals lose electrons, and that results in giving you a noble gas type of electron configuration. The non-metals will gain electrons to try and achieve that noble gas. So these elements either gaining or losing electrons to achieve that noble gas configuration is pretty common. And the reason for that is we talked about how noble gases are pretty unreactive. They're not totally unreactive, but they're pretty stable. And so these these elements and these ions are always trying to reach the state of which they're the most stable. The other thing I want to point out is that transition metals, notice we haven't really talked about those yet, those don't follow the octet rule. And that's why we haven't really talked about them much. Transition metals lose the valence electrons first, then lose d electrons in order to get to whatever the charge is. So transition metals are a little different than the stuff that we looked at before. Remember, transition metals were the things that weren't talking about. So we had that 1 through 8A that didn't include any of the transition metals. So as I said in the beginning, when we were talking about the 3 types of bonds, is that covalent bonds are by far the most common. And in covalent bonds, what you're doing is you're sharing electrons. So those ionic compounds we talked about, you're having the cations donate electrons to the anions. So the metals donate electrons to the nonmetals. In covalent bonding, there's no donating, it's just kind of sharing. But what we'll see is, in a bit, is that the sharing isn't always equal. And we have some terminology describing whether the sharing of electrons is equal or not. And if it's not equal, how unequal is it? Covalent bonds also are what you study in organic chemistry. And most stuff has carbon in it, which is kind of the definition of organic compounds, which is the definition of organic compounds. And so that's why most of the reactions that we really are concerned about involve covalent bonding. So there's several interactions that are going on in this. So we have the attraction between the electrons and the nuclei. So that's that negative charge on the electrons attracted to the positive charge in the nucleus. Then we have the repulsions between electrons. So that's that negative repulsion. And then we have repulsions between the nuclei. So in that case, it's a positive repulsion. So we haven't talked too much about that, but when we start talking about this bonding, that does come into play. So in order for the bond to actually occur, you need to have the attractions be greater than the repulsions. So that kind of makes sense. The other thing I want to point out here is this picture on the right-hand side, the B part, where you see that the concentration of electron density is between the nuclei. And that's what we're talking about when we talk about a covalent bond. It's that concentration of electrons in between the 2 nuclei there. And that's the bonding distance. That's all that kind of stuff we've been talking about. That's what you're getting at. And so we'll talk about that a little bit more. And we'll talk about how we use Lewis structures to demonstrate that. But for now, I think I'm going to stop here and we'll pick this up next week. And so just to remind you again on the quiz, at the tail end of the quiz, there are some questions about writing reaction equations out. Just use an equal sign to separate the reactants from the products. Don't worry about finding an arrow. So that's it for now. I'll let you start the quiz unless someone has a question. Okay, thanks. Good luck on the quiz.